Oh, thank you. So thank you for coming to this talk. And so actually today what I'm going to show you is not quite about program construction, but still more about proving a certain certain properties of a program. And so what I'm going to show you today is just a small puzzle. And because in the later part of my career here, I tend to like to solve small puzzles. And this is the one I find interesting. And also, so I came upon this puzzle a while ago, and I enjoyed playing with it a lot, and I'm not sure whether it would be substantial enough to be developed into a full paper. But however, I decided to talk about it here because I think it's fun, and I also think it's tricky enough to have something to talk about, but not so complicated, such that I believe everyone here will be able to understand what I'm talking about. Okay, so the problem is about dragon curve, and in case you haven't heard of dragon curve, so this is how a dragon curve is like. I believe that this one is a order 12 dragon curve, and with complex beautiful pattern. And this dragon curve is probably one of the most well-known of those recursive curves, which were developed when people were studying fractals. And so how do you construct a dragon curve? Let's do this. Okay, so right. So this is a level 1 dragon curve. Just one single line. I think it's order 0 dragon curve, just one single line. Then one of the way to construct dragon curves is to start from this one. And also, sure, you imagine that this one has a beginning and an end point. Okay, so to go from this level to the next one, you make a copy of it and then spin the copy. Sorry, let me rotate on. Okay. So you spin the copy around the end point, 90-degree clockwise. And that's a order 1 dragon curve. Let's do this again. So right, you make a copy of it. Sorry, and now this is the beginning, and this is the new endpoint. So you make a copy of the entire graph, then spin it around the endpoint 90-degree clockwise. That's the next dragon curve. Again, so copy.
So always the end point of the copy is always the end point of the next one. And
the end point of the copy. But so before this is the beginning and this is the end point. From now afterwards, you you rotate the copy around the end point. Now this becomes the new end point, right? Okay, so let's do this again. Copy and right. Make another copy. Rotate it 90-degree. Twice. Yeah, that's the next one. So just for fun, let's do this. Define again for the last time. So right now you can recognize that this is the beginning and this is the end point. So you make a copy of everything, rotate it 90-degree. Right.
We close the square.
Yeah, yes. So that's how those small squares in the previous picture come from. Okay, you keep doing that. So okay, that's one of the way to construct a dragon curve. But there's another way that if we still in this so in the first way, basically you always copy, you treat the entire graph as one big thing, and operate and copy them and rotate them as a whole. In the second approach, you deal with each individual segments of the picture. So now, still similarly, this is the order zero dragon curve. And what we are going to do now is that whenever we see this, whenever we see a segment like this, we turn it, we replace it with two segments, leaning to the right side of this segment, pointing toward each other. Okay. So now here we have this order zero dragon curve, and this is the beginning, and this is the arrow is the endpoint. Okay. Now we imagine that this is what this curve was, and then we replace it with two lines like this, and that's a order one dragon curve. Okay. Now to go to the next level, this the dragon curve was originally like this. We replace each segment with this. Okay. So what happens here is that now we have two lines going this way, and in here, because the arrow goes toward this direction, so now the two lines go this way. And if we remove these dotted line, now we have a level 2 dragon curve. So it looks like the previous one, but only with a small rotation. Okay. Then let's do this again. Okay, maybe I should make a copy of this here and scale it a bit. So this was the previous one. And now if okay, so there's an arrow going this way. So now the new arrow goes like this. And this way, so the new arrows goes like this.
So it's like if you're looking towards the head, you go on the right side.
Yes. And so basically, so that's why the direction is important. And now, okay, the direction is like this. So the new smaller segments goes like this. And finally, now this one has a direction like this. So now the new arrows are like this and this. And now if we remove these black lines, okay, we get this essentially the same picture, right? And I won't do the next one because it's too much. Okay, so what's happening here? So these two approaches are supposed to give you the same picture. But why? Okay, one way to understand that, if you haven't seen this before, is that if you take a piece of paper, then you fold it in half, fold it in half again, and maybe let's fold it in half again, always toward the same direction. And then if you unfold this paper, the shape you get is the dragon curve. Okay, so now you can see that the first approach, which we call the unfolding approach, works because basically every time we make a copy of the picture, it's basically doing this kind of unfold, right? And then the second approach is basically folding this paper again. And so that's why you replace each segment with a segment looking like this. Okay, and so now this is a physical proof that you get with this approach you get the same picture. But however, of course, we are not done with it. I want an algebraic proof that these two approaches actually give you the same picture. So to do that, we have to do a proof. To prove that these two approaches give you the same picture, we have to first represent this dragon curve using some data structure and come up with two programs simulating these two processes of drawing dragon curve, eventually proving that they are the same function. So this is what we're going to do today. And so firstly, how do we represent a dragon curve? Okay, so one of the ways to just represent the curve by the way it turns, the direction it turns. So now, if this kind of turn is a left turn, and whereas this is a right turn. Okay, then let's do this here. So when you go counterclockwise, it's a left turn. When you go clockwise, it's a right turn. Okay, hope you can all read this. Okay, so now this all the zero dragon curve is represented. So a dragon curve is represented by a list of left and rights. And this all the zero dragon curve is just a empty list. Then all the one dragon curve is what? Okay, it's just an arrow. Okay, and what about this? This order two dragon curve is a left turn and a left turn and the right turn. So it's L, L, R. Okay, let's see the next one. Remember, this is the starting point. This is the end point. Okay, so there's the beginning, the initial segment always repeats the previous one. So if again we have L, L, R, like L, L, R, and now what? There's a left turn. This one I'm using a different color. So R, and now here I'm using a different color. There's a left turn, and left turn. Sorry, I'm going to move this a little bit further. And then now what's going to happen? So this, yeah, looking at, I would get confused. So let's look at the cheat sheet there. This is clockwise. So counterclockwise. So it's the left turn.
And then right.
And the right turn. And the right turn. So it's L, R, R. Oh, we don't see any pattern here. Actually, okay, maybe it's this one is getting more complicated. So just look at this one. So every time when you go to the next level, what happens? So you copy the previous one and then put an arrow in the middle. What about this? This is actually the same sequence reverted and then inverted. By inverted, I mean changing every arrow to an R, changing the R to an arrow. So because LLR reverted is RLL. Then if you switch every R to L, L to R, you get LRR. RR, LRR, RL, RLL. Okay, anyway. But why is that? Because actually, when you, so of course, this one is the exact copy of the previous one, whereas this one is actually the same graph, the same picture going backwards. So this one was the same picture, but however, now the beginning of the ending point becomes the beginning point. And the previous endpoint becomes the beginning point becomes the end point. So it's going, the same picture going backwards.
Oh, because you rotated it this way and then stuck it in?
Sorry?
Because you rotated it this way and then stuck the end on the beginning, basically,
Yes.
when you,
Yes.
and that's why it's going backwards both ways.
Yeah.
Okay.
So it's like you go through the end, this is a maze, then you go to the end, then you go backwards again, right? So, okay, so let's, if you write the program to do that, it's a root. So
the rotate 90 degrees is the L that you stick in the middle.
yes.
And then you're going backwards. The copy ended up going backwards through is the
Yes.
reason why all the reverses.
Yes, indeed.
Okay, okay.
Yeah, so that's the reason you have the L in the middle, because it rotated by 90 degrees. Clockwise. Clockwise, yes. Right. And if we had time, we're going to generalize that. You wonder why always an arrow in the middle? Why is it possible to generalize it to both L and R? So we are going to do that if we have time. And so, okay, the program is like this, that there's a data type, a term is either L or R, and this function inf turns the L to R, turns the R to L, and this dragon U, where U means unfold, does something like this. Okay, this natural number is the number of times you do the unfolding. And when zero, you just stop with the empty list. Otherwise, the input one must be one plus something. So you recursively call the result t's turns, and you in the beginning is always turns. Then you put an L in the middle, and here you do reverse of t's before netinf. And this function is called dragon U. How do you implement the function that construct dragon curve the other way? Okay, what's happening here is that it's a bit difficult to see, but okay, what the thing we get is, so now instead of, so let's maybe let's make a copy of this here. The first one is empty list. The second one is L, then L, L, R, then L, L, R, L, L, R, R. And basically to go from one level to the next, we want to model the process as doing something to each of them or doing something next to each of them. So it turns out that what happens here is that you make a copy. So from here to here, you make a copy of, from here to here, you make a copy of the previous one, and then insert LR, LR between them. And then also to go from this one to the next, what do? You first copy the previous one, L, L, R, L, L, R, R. And then put L, R, L, R, L, R, L, R between them. So let's check. So you start with an L and the L, yes, and the R, yes, and an L, L, R, R, and so on. So to understand why this is the case, actually it's easier to understand in terms of pictures. We have time to explain that. Okay, let's see. So you see, this is one piece of paper. And then after you fold it once, it becomes something like this. And then what happens is that, so after now, if you fold it again, let me see, it's something like, something like this. And so you can see that the every time you go from here to here, so these black ones are these, the black ones are this. The black ones are this. And then they should be the same as they should be the same as the previous level. Oh, sorry. this is an arrow, and this is a arrow. Oh, what's happening here is that so every time you go to the next level, so this ones stay the same.
That isn't the first L the one of the.
Yeah,
Oh, you're right. Sorry. So, okay, I can explain this well. It's clear when we have a picture of this.
it seems like when you fold it in half, the new fold is the LR that's on the right. Like that's the new fold that you got.
So, okay, can you say that again?
The RL that's on the right-hand side, that's the new thing that happened when you did the fold.
Yes.
Right, just like Shin was saying, the L on the left is the L that was on the right in the previous go.
Right.
And then so what we did is we added that fold. So we added an L and an R
Yes.
sort of in between every fold.
Yes. Exactly. Thank you.
So
So,
like coming from like the third thing to the maybe the next level is like draw a straight line
Oh, yeah.
and cutting through each
Yes.
seed.
yes, exactly. So, you do another fold, it's like cutting a line. Yeah, so that's why you add, that's why you add this LR, whereas this one and that's already there should stay the same. Right. So, so to do that as a program, so now we,
And the reason it will be LR is the first one was going this way and the piece of paper on top of it is always kind of going the other way.
yes,
So that's why one becomes an L and one becomes an R and then things.
yes, right. So, okay, to do that, we define this dot function dragon E, and the E means expansion, and it's probably not a good name, but because it means that one segment is expanded into 3 or 2. But however, anyway, that's how we currently call it. So it's also a function from natural numbers to a list of terms. Okay, this all should be lists. And so in the base case, you get you just return an empty list, and then in the inductive case, when the input is 1 plus n, you always compute the previous level, and then now we define this function, which I call interleave. It's like interleaving two lists. However, it's not quite interleaved because these two lists are not exactly symmetrical. So that's why I denoted using a asymmetrical infix operator, because there was this advice that you only use, so when the binary operator is not symmetrical, then use a asymmetrical symbol to denote it, right? And so this LR is an infinite list, a string of L and R's. And LR is L cons R cons LR. And then this interleave symbol takes a string of things and the list of things, and then interleave this string into every between every element of this list. But you start with a string, and you always end with a member from the string. So when you see an empty list, you return this singleton list of X. Otherwise, this list must be empty, so it can be split into head and tail. You take the first element of the string, and you take the first element of the list, and then you recursively, inductively, interleave X's into Y's. And then dragon E is repeatedly interleaving LR into the previous level, previous order of dragon. And now the task is to prove that these two functions are actually the same. How do we do that? Okay, so let's
Try it for 1, 2, 3, and 4 and figure It's only got 2 lines in it anyway, so if it works for the first 4, it probably works for all of them.
Yeah, 100% code coverage.
100% code coverage.
No, we prove everything by induction.
Oh,
Basically, the only way I know how to prove things is by induction, and that helped me through my career so far. So then, so to cut the long story short, one of the way to show that these two functions are the same is to show that they actually they satisfy the same recursive equation. So if we can so now we have this, we know that dragon use is defined this way. Dragon U is defined this way. If we somehow know that, be sure. Okay, if I'll draw this down. This is dragon U. If we can show that dragon E also has this pattern, meaning that okay, I will make a copy of this. This was dragon U. And if dragon E also looks the same, meaning that dragon E of 1 plus n equals dragon E of n, append T, append map inverse of reverse of dragon E n. Okay, if we can prove this, then we're done. Okay, shouldn't be too difficult, right? And so, how do we prove this property? Let's say, like I said, the only way I know how to prove things is by induction. So I started with, sorry, this is not a T, this is an arrow. So I started with induction on what? Maybe on this, on the only argument here, this natural number n. So when n is 0, things are easy. So then let's try. So let's see what happens when n is when we replace n by 1 plus n, which makes this 1 plus n 2 plus n, and then a dragon E 1 plus n, append arrow, append map inverse, reverse dragon E of 1 plus n. So now we will prove this, prove that these two are equal, assuming that this star property holds. Okay. So a person I admire a lot called Rob Hintz once said that program derivation, program calculation is not a spectator sport. And I think what he meant is that usually it's not fun watching it. You usually have to do it yourself to enjoy it. And I enjoy doing this a lot. And however, in talks, I have to show this calculation to people. So I would invite you to imagine that you are doing this together with me, to enjoy, to share fun together. And so, okay, what's happening now? If we recall that Okay, what we usually do now is to just, there's nothing I can do here apart from just expand this by definition, which is LR, interleaved with dragon E of 1 plus n. Now, yes, use induction, right? And this is the crucial step of using induction. So, which gives us, wow, LR interleaves into dragon E. Append L, append net inverse. I'm abbreviating to L to ref. Reverse dragon E of N. Yep, that's it. And we clearing this up. And now what? What I usually tell people is that when you do calculation, always have a purpose, always have a goal. Don't manipulate expressions blindly. And we know that eventually we want to, this is n plus 1. We want to know, we know that eventually we want to come up with this. This is our goal. So, and dragon E1 plus n, what is this? It is LR interleaved into dragon E of n. So the goal is somehow taking this and then distribute this into this expression such that LR interleaved touches dragon E. So then we can fold everything back. That's our goal. Okay. So always have a goal. Then
So should we just go up from the bottom line for our first step?
sometimes I do that too.
Yeah.
When expressions get too complicated and I don't want to do it, then sometimes I go backwards and see how they meet in the middle. But however, when presented to people, I always pretend that I go from top to bottom to show that I'm smart. Right. So now we need to think about, but in this case, for the next step, I think it makes sense to go from top to bottom. Because now what we should think, because now we know that our goal is to distribute LR interleaved into this expression. So what we should do is to think about what happens when an interleave meets appends. What happens when you interleave something which is when you interleave a string into a list which are things appended together. Okay, in the special case, when this list is LR, you have this property that LR interleaved into these three things together is that this is a distributivity property we want. That is LR interleaved with X's with Z in the middle unchanged, and LR interleaved into Y's, provided that the length of axis is odd. And when the length of axis is even, there's another property. There's another similar property we can come up with, but we don't need it today. Okay, so to understand this, there's an example. That's how I understand that. So when LR is interleaved into ABC and Z, append DE, is LR, and actually happens to be that because ABC has an odd length, so it cuts LR at the right place. So it happens to be LR interleaved into ABC and LR interleaved to DE with Z in the middle. Okay, Yeah, good news. Okay, let's use that. And but by the way, also it happens we can prove that dragon E of n when n is not zero always give you a list of odd lengths. Right. So okay, so now we have what? We have LR interleaved into dragon E.
Do we know n is not 0?
No, we don't. However, we can when it's zero. That's an easy alternative base case.
Okay.
Okay, and dragon N. Ah, good.
Dragon of n is all that's what matters. Because you will always
Yeah.
have
And LR.
2 odds plus 1, so the whole list is odd.
Unless it's 0, though. It's gonna be the empty
No,
list.
no, the theory that he had up there was that you can distribute this if the list is odd.
If dragon E of n is odd,
Yeah, exactly. It's it.
but dragon E of 0 is the empty list.
Yes. So that's a special case,
Yeah.
which can be
So
easily.
that's separate.
Yeah.
It's easy to prove actually.
Okay, so now we have this, and this folds back nicely into dragon E of 1 plus n. So okay, we are maybe 33 or maybe 33% done. Okay,
95 actually. because-
95 really?
Yeah.
Not an infinite amount of it when we used induction.
No, I mean that because inversion and reversibility do not change really anything for the insertion.
Exactly.
Yeah.
So yes, that's the other property we're going to need later. And because this falls back nicely into dragon E of 1 plus n, which is what we need. And append L is here. That's fine. Okay, now we have LR interleave into this. Okay. Firstly, what happens when LR interleaves means map inverse. Interleaving is a natural transformation.
Ah, okay.
So it has this nice property that doing map to it doesn't. Okay, if we do map to both sides of things, doesn't change its value. It's like if we do for any f, map z of z interleaved into map z of axis is simply map z of map f over map f of that interleaved into axis. You can do the interleaving first before do the map. However, what we have now is that we don't have this. What we have now is that this f is inf, and here there is no map f. But actually, this one can prove this easily that from this naturality property, we can prove this property easily by map in after map in is simply identity. So we have that z interleaved into map in of something is okay. This looks quite awkward, but however, it's yeah. If you do that on paper, is that before I could just read it and understand it. Now I have to do that on paper. But probably many of you are much younger and brighter than me, so you should be able to see that just by looking at it. Okay, so now what's happening here is and that gives us map in outside, that leaves the map in outside of the expression. So that's the good news too. So now we have map in here, which looks like here. Good news. And instead here we have map in of LR interleaved into reverse of dragon E. Of M. I hope you can read my handwriting. So now we want to turn this into this. Is that right? Okay. So let's think about what happens when interleaving meets reverse. And then it turned out to be that, okay, there's another property that if you interleave LR into axis and then revert it, it's the same as revert axis first, and then interleave RL into this. Map inverse LR is RL. You start with R, then L, then R and L. And you can see that by one example. This is ABC, and LR interlinked to ABC is LARB Then if you reverse that, you get this, which is CBA interleaved by RL. And that works when the length of axis is odd. By the way, all these properties can be proved by induction. Okay, so that's a good news too, and that happens to match our expression pretty nicely. So we have that allows us to, let me copy this here, dragon E 1 plus n and L map inverse. And here, okay, now that allows me, the property just now allows me to lift reverse outside and push LR interleave inside next to dragon E of n. And this is dragon E of n plus 1. So we are done. I was quite happy with that when I did this. But then actually, this thing was good. We still have time, and this was so this small puzzle was proposed to me by a student, and so he actually considered a slightly more generalized version. Like in the beginning, we might be wondering, why do we always put L in the middle? Isn't that a bit artificial? No, of course it's artificial. But so can we generalize? So that's because we have L in the middle because we always spin the graph clockwise. So what if instead of taking a natural number as an input, we take a list of instructions as input? So we tell the computer to rotate the picture counterclockwise, clockwise, or counterclockwise in each step. And so when we spin the picture clockwise, we put an L in the middle. When we spin the picture counterclockwise, we put an R in the middle. And so yes, that's what we are doing here. Okay. Now we introduce another small data structure, rot rotation, which is Cn, having two values C or D, where C means clockwise, D means counterclockwise, because I cannot find a good alphabet, which doesn't, yeah. So, or actually I could probably just reuse L and R, but I think that's probably more confusing. So anyway, so now this generalized dragon U takes a list of rotations and gives you and returns a list of turns. It's similar to the previous one. And now you take a list of instructions and do each instruction from left to right. Okay, and then when you, like I said just now, when you turn clockwise, you put an L in the middle. When you turn counterclockwise, you put an R in the middle. And what about the other way of construction? It turns out that you need to perform the sequence of instruction backwards because it's more like a bottom-up construction. So when the last instruction is clockwise, you interleave LR into the previous graph. When the last instruction is counterclockwise, you interleave RL into the previous graph.
Like pulling the paper to the left or
Yes,
forward.
yes, exactly.
Or duplicating the red and then turning it back to the left or the right,
Yes,
which matches the things up to show.
yes. Good. Yes.
Yeah.
And actually, the previous definition of dragon U and dragon E are essentially folds on natural numbers. Okay, because the function's value, the value function on 1 plus n is defined on the value on n. So it's a fold on natural numbers. And the new generalized definition, dragon U is basically a fold R. People know what it is? Okay. A fold R is
Like a folder, like, you know, the thing you put the papers in?
no, unfortunately not. And a fold R is something like this. Do I have a definition here? Yes. Right. A fold R takes a binary operator and then then process a list using a binary operator and this base case by grouping them from by grouping the left ones first. So fold R of O plus and E of ABC is A O plus, B O plus, C O plus. Oh, that's it. So that's the base case E. Why is it called fold right? Maybe because we break it from the right. Okay. Whereas fold left does the dual thing. So fold error of O times of E of ABC is let's see, it's E O times A, O times B, O times C. It breaks the list from the left. And then it turns out that dragon E is a fold, dragon U is a fold right. And dragon E is a fold left. You can see that by the fact that dragon U always take the rightmost instruction first. And dragon E always takes the leftmost instruction. So dragon U and dragon E can be defined by fold R or can be defined in terms of fold R and fold left this way. And dragon U is fold R of O plus, where O plus is defined like this. And dragon E is fold left, where fold left of O times, with O times defined this way. Then to show that these two functions equal. Yeah, they're still equal. There's a general theorem which I've found in Richard Bird's textbook. It's called second duality theorem, which says that a fold R of O plus of E equals fold left of O times of E if these two property of O plus and O times holds. The first one merely says that the first one is about the base case. And the second one allows you to turn three things bracketed from the left to the next one allows you to turn things bracketed from the left into things bracketed from the right. So it says that if you have three things, X and Y and Z, doing O times first, then O doing O times first, then O plus is the same as doing O plus first on the first two, then O times. So in this case, we want to show that so in this case, when we want to show that dragon U and dragon E are equal, we want to show that this particular definition of O times O plus satisfy this. Right, and okay, let's try that. What does that mean? Okay, so let's see what the left-hand side is. Let's see what this is. That means for every C, a small c, that CO, that means PS and PS O plus Y, let's see. Sorry. C O plus PS O times B. What is that? Is let's expand this. So it's PS append. This can be L and R. So depending on what C is. So let's just put a small L here. Append the map inverse and reverse T's. And okay, it should equal what? It should equal XO plus Y O times Z, which is
The O times is this.
yeah, sorry. I forgot this. And this. So that's only CO plus TS. And then the whole thing that this is, let's assume that this is just look at special case. There are interleaves. Okay. And then what about this one? It's again, sorry, I'm just copying it. So that's C plus Y TS O times D, which is what? Which is, so now this is LR introducing to TS. And then it should be the same as this. NL append map inverse of ref of LR distributed to TS. And does it look familiar?
Same as we just proved.
Yes, that's what we have just proved.
Yeah.
With a slight generalization. Right. So okay, we're done, and I'm happy with this so far. So that's about what I'm that's all I'm going to talk about today. And there's other interesting properties of dragon curve, such as that this curve never overlaps. So they touch. You can see the point touching each other, but however they never cross each other. And the property also holds when you allow arbitrary rotation. And that can also be proved. And so it's being done. It has been done by people before. But however, I think we can do that. We are trying to do that in our notation, our way, and I think it's fun as well. But I won't be able to talk about it today. So okay, that's all I'm going to talk about today, and I hope you enjoyed it.
Thank you.
As much as I can.
You get any personal?
Just I love geometric and algebraic connections, you know, they're like, you know, you can draw something and you have an algebraic representation. the specific rotations here, so that this specific algebraic property reminds me a little bit of quaternions. Just I get this similar vibe of like, you know,
You just remind you of what?
quaternions, because they have like anti-commutativity and like, you know, their rotations and like, you know, clockwise, counterclockwise matters. And I just like, I'm getting that vibe a little bit. So I'm curious if there are any extensions of dragging curves in non-planar. Like, so right now you have just planar curves. If I want to go to 3 dimensions, is there some kind of natural extension that goes to 3 or higher dimensions?
Non-planar, do you mean extending to 3 dimensions?
Yes. And like,
Yes, there is such a generalization. And I can't recall the details, but yes, actually there are many variations of dragon curve. So from the way they are drawing, that they are drawn. So here we always turn 90 degree. And but what if it's not 90 degree, but different angle that people have tried that before. And so this is it's not your question, but there's an interesting property that when we turn 90 degree, then this picture doesn't overlap. And then when we use 100 degree, the picture doesn't overlap. However, when it's 94, 95 degrees something, then we can see the points where they touch each other. And so people are puzzled why. And then probably there was some later development explaining why. And then there's also a separation of spinning, not only this dimension, but to another dimension. Yes.
yeah.
So now there's a lot to explore.
Okay, very cool, very cool.
You mentioned earlier today that you like to start with pen and paper and then eventually switch to Agda. So I'm wondering, for this problem, how much were you able to do with pen and paper? And when did you start typing in Agda?
So all this were done on paper. Yes. But however, actually the thing is that a student of ours found this topic first, and then he did all the proofing Agda because he was supervised by Liang Ting, an Agda person in our group. And then I look at it, and then I thought, in his case, I feel that he was probably somehow too trapped by the detail of Agda, that he couldn't see things more abstractly. So when I saw his formulation, I kept thinking, look, there must be a more abstract way of doing this. So then I rewrote everything using more combinators, using map, inverse, and then using the properties of them, and then simplify his proof. Then he did his proof again in Agda. So then I think for me, I don't know. Sometimes it happens to me too that when I use tools like Agda, I got to trapped in details, and then somehow if I then I got stuck, and I see all the symbols on the screen, and I cannot read them well. Then so I need to step back and then start to work on paper. And sometimes that, in many occasions, that really helped.
So I wonder, because like when you finally express things using list and discover that one is a full left and the other is a full right, that leads to the observation that the second duality theorem you wrote above actually generates the like inductive proof obligation when the proof is directly done by induction. I wonder, does that mean like some natural number induction programs, some natural number induction problems are things like this association are actually things that has the same pattern as this like the reassociate proof obligation. Like the thing like pushing things inside in maybe in some induction proofs are actually special cases of this second duality theory, where things are like ones, but one from the left, the other from the right.
Okay, firstly, this Because the second duality theorem itself is proof by induction.
Yes.
And so we can see the proof of this as a generalized case of many other proofs.
Right. Oh, maybe a way to rephrase it, my question is whether actually some induction problem ordinary natural numbers has hidden structure where they were actually can be phrased in terms of like full left and full right. It's just that this pattern is invisible when we only look at natural numbers.
So like the gap between the two definitions of the dragon functions where one, you're pulling from the end of the list, the other pulling from the beginning of the list. But when you do natural numbers, you always pull from the,
Yeah, you always just decrement the number.
Yeah, it could be, and because as you know, natural number is a boring list.
Yeah.
Where,
right, pulling from the back at the same as
Yeah.
pulling from the front.
So actually, then in the next, so in this for the natural number case, it doesn't matter which direction you start because they are all the same. So actually, all that matters is the length. And then once you generalize it to actually what happened, well, what actually happened when we played around with this was that we generalized this from natural numbers to lists. Then we try to show that so initially we thought both of these are fold R's. And then we tried to prove that they're the same, but we didn't go through. Then we coded in Haskell and run the program and realized, oh, actually they are different. However, if we do a reverse, then they are the same. So so actually I was wrong. One is fold left and one is fold right. So then, so it turns out that in the generalized case, the extra information you put in the list matters, and then so the order matters. And I think your question is a more general one. So is it? I think it's probably is your question that could there be some properties of natural numbers turn out to be could there be some properties on natural numbers whose order matter?
Yes, some sense of order actually is being hidden.
Yeah. So I'm not sure because still a natural number is a. Okay, one thing I thought of was another of our previous another thing I've been working on, which is about top-down algorithms and bottom-up algorithms. So so both algorithms do n iterations. And however, one algorithm decompose problem top-down, the other performs the calculation bottom-up. So the directions are different. And then so then to prove that these two algorithms are the same takes lots of effort. So probably it is like one of the case you talk about that. So both are iterations, but however they work two different directions, and then we need to prove that they're the same. So probably it's something like that. Thank you.